Okay, yes, now we are live. So this week in the 3D seminar, we're very lucky to have Daniel Ritchie from Brown University. So let me first give a quick introduction of Daniel. So Daniel is assistant professor of computer science at Brown, where he co-lead the Brown Visual Computing Group. And Daniel works on the intersection of graphics with AI and machine learning, build intelligent systems that understand the visual world and help people to be visually creative. So Daniel got his PhD from Stanford, worked with Pat Harahan in the graphics lab and Noah Goodman, and did his undergrad at UC Berkeley. And Daniel's research has also been funded by Adobe, Autodesk, Pixar, NVIDIA, and has been, as well as grants from DARPA and NSF. And also very recently, Daniel has won this NSF Career Award. So today we're going to hear from Daniel on neurosymbolic generative models for structured visual content. So yeah, Daniel, please, thanks.
Great. Thanks for the introduction, Jajin. Appreciate it. Okay. All right, well, thanks everybody, everybody out there in YouTube land. So I'm gonna tell you about kind of a direction of research that my group has been doing for a little while now. And we maybe didn't quite realize we were doing this direction of research, but I've kind of since figured out like what exactly is going on here. And that's something that I'm pretty excited about, and I want to try to get other people excited about as well. So I'm going to be talking about generative modeling of 3D stuff. So probably with the crowd that's out there listening to this talk, I'm preaching to the choir, but I do want to make sure we're all on the same page about the motivations for why we care about doing this, about generative models of 3D things. And so I'll talk about a couple of different application domains. So first, there's reasons to care about this in graphics, which is kind of my home discipline. One is that these generative models of 3D objects and 3D scenes and things like it really enable pretty amazing capabilities to explore design spaces. So if I'm an expert designer and I want to explore the space of potential automobile designs, or if I'm someone who's maybe not expert, more of a novice designer, but I want to be able to create 3D shapes and without having to resort to using really complicated professional 3D modeling interfaces, these kinds of tools are pretty transformative. And then they also have a lot of applications in creating content at scale. So all of the films, visual effects, games that we're all playing these days are getting bigger and bigger, more and more massive virtual worlds, and people who are consuming these experiences also expect them to be high quality and realistic. So it kind of becomes unreasonable to expect that a person, an individual 3D modeling artist is going to pay attention manually to every single 3D asset in these environments. So being able to sort of generatively populate these worlds is also pretty important. And then if we kind of step to another discipline and talk about their use in artificial intelligence, these kinds of generative models can be really strong, really powerful priors for autonomous vision systems. Some kind of agent that's trying to perceive the world through like a 3D scanner, and it receives some sort of incomplete 3D reconstruction of an object like these ones. If I have a generative model of 3D objects and I condition it on these kinds of observations, I can often use the priors that my generative model has learned about things like structural regularity and symmetries to infer sort of what structure must have given rise to these observations. Another interesting application is using generative models to produce training data for AI agents. So that could be producing labeled images for indoor scene understanding, but also to produce entire virtual environments for training autonomous agents to do things, for example, in our own indoor spaces. So this is another kind of compelling application for these tools. All right, so that's why we want to do this. So how has this been done in practice? How have we built generative models of 3D content? And not surprisingly, the kind of the history of what technologies have been used has really paralleled the broader history of artificial intelligence as a discipline. So if we look back in the early days of AI, you had people have probably been familiar with this acronym GO5, good old-fashioned AI, where these early AI systems were based on lots of rules and formal logical reasoning. So what I'm showing here is a little video recording of Terry Winograd's Sherdloo system, which would receive as input a logical description of a bunch of little physical objects like boxes and pyramids and stuff. And some were stacked on top of each other and some were inside of each other. And then you as the user could pose queries to this system, and it would be able to use logical reasoning on this representation of the scene to answer questions. So for example, I could ask it something like, what does the box contain? And it will tell me it contains the blue pyramid and the blue block. This display obviously is not showing the colors, but these objects do have color attributes. What is the pyramid supported by? Well, it's supported by the box because that's what it's inside of. And nowadays, of course, everything has sort of been taken over by statistical AI. So earlier, kind of in the early days of this, we had things like probabilistic graphical models, and nowadays, deep nets kind of rule the world. And so we have kind of modern versions of the same kind of problem that Sherdloo is trying to solve, which are now being tackled by people using things like the Clever data set, where we have images, a vast array of images like this, which are paired with questions and answers. And just from these kind of paired image, question, answer data, we have neural networks that can reasonably effectively learn to answer these kinds of questions, purely from learning statistical patterns, right? So if we look at 3D generative modeling as kind of a subdomain of AI in general, it has mirrored this history, albeit on a more compressed time scale. So in the early days of people in graphics pursuing this goal, we had a lot of procedural or rule-based modeling systems. So this dates back to things like Aristide Lindenmeyer's L systems for modeling natural structures like plants. And even more recently, there have been systems like this one. This is from around 2000 or 2001, a paper that occurred at SIGGRAPH called Word's Eye, where I could provide a natural language description. John uses the crossbow, he rides the horse by the store is under the large willow, etc. And some kind of underlying constraint solving system would then automatically produce a 3D scene which was consistent with that description. But it was all based on rules that had been hand coded to say, what does it mean to ride a horse? What does it mean for a store to be under something? All of this was manually specified. And so, unsurprisingly, since then, statistical methods have taken over. I'm kind of skipping over a lot of stuff that was done with more classic probabilistic graphical models and things of that nature, and jumping to kind of what rules the world nowadays, which are deep generative models, things like generative adversarial networks that can spit out occupancy grids of where an object is in space, or can even do that with octrees or kind of spatially adaptive grids or point clouds, or you name it. There's many different representations and models that have been proposed. And so if we look at this, we kind of take a step back. What we see is that there's been this transition from methods that were based on symbols, so rules, logical objects, things like that, to neurons, right? All of the kind of the units, the distributed processing units that are in these big deep neural nets. And so in thinking about this transition, there's a couple of questions that I think are important to ask and answer. So why did this transition from symbols to neurons happen? And have we actually lost anything by abandoning symbols and going sort of full on with the deep generative modeling approach? So with this first question, why did the transition to neurons happen? There's actually kind of a lot of philosophical arguments that often get tangled up in this question, where certain people are saying, well, this representation is more like what happens in the human brain and blah blah blah. I'm going to sidestep all of that. I'm going to focus purely on the kind of the pragmatic aspect of what works in terms of producing good results, generating good-looking 3D structures. And so I would argue that the first reason for this is the ease of actually creating or authoring these generative models. So if we look back at the sort of earlier approaches of procedural modeling, where we have these symbolic programs that describe how to generate some class of geometry, these are kind of hard to author. You need to have programming skills in order to write a program that does something like splits up a parcel of land and turns it into some set of buildings. Whereas by contrast, these deep generative models, they're relatively easy to author in the sense that, if somebody hands you a general purpose, deep generative modeling architecture, you really just sort of have to add data. I train it on a data set of, say, chairs from ShapeNet, and I get out, outputs that look similar to my training data, but hopefully have generalized in some interesting way. So just adding data is a lot easier than having to write these procedures. The second reason I think that the neurons have taken over is in terms of what variety of outputs can the method produce. So these procedural models really do have a limited output variety in the sense that they can only output structural and geometric variations that have been explicitly coded into the program. And so you might imagine it's kind of hard to write a single program that might output all possible cars. So here I've just taken a screenshot from an open source repository where someone has written a little procedural car generator. And yeah, there's some variety here, but you start to see a lot of repetition, right? It's difficult within a single rule set to capture all of the variety of car shapes that actually exist in the world, right? Whereas on the flip side, these deep generative models, really any kind of 3D entity can be modeled as long as you give it the right training data. And so we can already see when trained on a data set of cars, we get a lot more sort of realism and structural variety than would have existed in this data set. Okay, so the fact that it's just add data, easy to author these deep generative models, and that they can kind of capture a huge, potentially unbounded variety of shapes, that seems really appealing. It makes sense why these deep generative models are really taken off. But we want to be a little bit reflective and ask, is there anything that we've missed out on by sort of abandoning these procedural or rule-based approaches? And I think that there are, and one of them is that these procedural systems have this nice property that they always output high-quality geometry by construction. So here's an example output from, I think this is like a Maya plugin I found online that'll do procedural building generation. And you can throw different random seeds at this thing. You can give it lots of different tweaks, and no matter what, it'll always spit out good-looking architectural geometry. It's sort of not capable of producing some kind of garbage output shape. That's just how it's coded, right? It's programmed such that it can only generate a certain class of really high-quality output geometry. And if we contrast this with what we often see with the deep generative models, is that these things are typically riddled with errors in terms of their outputs. Many of these generative models are these latent variable models where we start with some latent code in some normally distributed latent space, and then we decode it into an output shape. And there often are very many bad pockets of this latent space where if you sort of explore around in it, some regions of it will decode to reasonable looking shapes, but you move a little too far afield and all of a sudden you get artifacts in your decoded shapes like blobby geometry, missing pieces, floating parts, all kinds of stuff like that can happen, right? Because there was no programmer who went and said, no, this is the kind of geometry you can generate. The network is learning it through statistical patterns, and so occasionally it doesn't learn the right thing. The other aspect that I think is important to call out is the interpretability and editability of programs. So not everyone is a programmer and can read and edit code, but often these procedural models do expose a lot of useful, understandable and editable parameters. So here's an example of a procedural model of a chair in Maya, which exposes these parameters for things like the tilt of the back or the width of the chair, things like that. These are useful parameters that a user might want to be able to manipulate. And it's nice to be able to understand when I look at this particular slider, I know exactly what it's going to do because I know what parameter of the sort of semantic parameter of the shape it controls. Whereas if we look back at our earlier video of this deep generative model that has this kind of, this sort of entangled latent space representation, yes, I can explore shape variations, but I don't really know what's going to happen if I kind of move in a particular direction in latent space. I don't know what changes to the shape it's going to make. And maybe it's going to change all aspects of the shape and not just one of them, right? It's difficult for me to understand what's going to happen when I make these edits. So if we take a step back and we look at these two, these two kind of questions, and I think it's worth then asking ourselves, well, can we get the best of both worlds? Can we somehow get a single approach to generative modeling of 3D objects that is easy to author, gives us a high variety of outputs, but also can provide some kind of by construction guarantees on the output quality, and that still allows us to edit and interpret the different parameters, the different modes of variability that each output actually has. And so if we want to get the best of both worlds, we want to look at actually symbols plus neurons. We want both of these in one representation somehow. And so that's what I've been thinking a lot about, this category of generative model, which would be a neurosymbolic generative model. So it's a generative model that captures a distribution of 3D entities using explicit programmed symbols wherever possible, because those are editable and interpretable and all of those nice properties. And then it uses deep neural networks wherever else, everywhere else that it needs to. So just to color code this for folks, I have the orange things. There's explicit program symbols, that's the symbolic part. Deep neural nets are the neural part. And so I'm going to keep this color coding, and I'm going to walk through what I think of as kind of the high-level pipeline of a neurosymbolic generative model. And then I'll show you some examples of recent work that I think falls under this category. So all of these are going to start with a deep generative model. This might be, a generative adversarial network or a variational autoencoder or something like that. So it's some, means of sampling from some distribution. But what it's going to produce as output, what each sample from this generative model is going to be, is not some output 3D thing, but it's actually going to be a program. So the deep generative model is going to generate symbols for us in some programming language representation. And then what we do is we take that program and we execute it. And what execution involves might vary depending upon the kind of program. It might be, some sort of simple, functional program that I can pass through an interpreter to get an output. Or the program might be more of a declarative program that expresses constraints. And so I might need some kind of optimizer or solver to actually execute the program. And in the course of solving this program, I might be able to say use a neural network to guide the solver to be able to find solutions faster. Okay, so I execute the program one way or another, and then I end up with some output geometry, and that's sort of the final output entity that I have from my generative model. Now, there are also going to be some systems where we'll then take this output geometry and we'll refine it, again, using a neural network to get maybe higher quality or higher detail geometry at the end of the day. So you can see that this overall pipeline, I think this is general enough to capture most of what's been done in the space to date. And you can see that there are, throughout the different stages, there are different, blue or orange boxes, with lots of different ways that neural components and symbolic components can interact. So let's look at a few recent examples of work that I think fits into this framework. And the first one I'll look at is a paper that came out of my group a couple of years ago at SIGGRAPH called Planet. And this was a system for generating indoor scene layouts. So given a empty room, fill it with objects. And so let's see the ways in which this kind of adheres to this neurosymbolic pipeline. So here's our kind of abstract pipeline. And if we kind of look at each stage of this pipeline, so there's a deep generative model here, which in fact, we did this via a graph generative model. So we started with a graph representation of an empty room with some set of walls. And this was a kind of an iterative generative model, which would repeatedly make decisions about, should I add a new node to the graph, where each node would represent an object? If I choose to add a node, like say a bed, should I add an edge connecting that node to some other node in the graph? In this case, it chooses to connect it to this wall. Each edge has some attributes about what the spatial relationship is between these nodes. And this process would repeat until at some point the generative model decides no more edges, no more nodes need to be added. So we had this graph generative model. And if we think about what this graph generative model is doing, it's outputting a constraint graph. Basically, these relationships, it is a declarative program that specifies that there are these objects in the scene and these relationships between them must hold. And those might be things about spatial proximity within certain directions, spatial adjacency, physical support, things of that nature. So once we're given this constraint graph, we then need to execute it. And in our case, what that looked like was a backtracking search algorithm. So kind of a standard thing that you would do to solve a constraint satisfaction problem. But it also had this form of neural guidance where we also trained these neural networks that could say, given that my graph tells me that there's supposed to be a bed, for example, that is adjacent to two walls, this little blob here denotes where I think the highest probability is for that bed centroid to be placed. And so this model would then allow us to make proposals within the search that would allow us to solve it more efficiently instead of having to do exhaustive backtracking search. So once we run that search to execute this constraint program, we end up getting a final 3D scene layout as our output. So that's one example of this kind of pipeline. Another one that's actually very recent is this paper that was actually just showed up on arXiv not that long ago, generative layout modeling using constraint graphs. So kind of a similar idea. They're going to train a generative model to produce a set of constraints that are going to describe, in this case, how different rooms in a floor plan layout should be related to each other, and then use some kind of solver to actually produce the final layout. So this is going to follow a similar sequence to the planet pipeline, where we start with a deep generative model. In this case, they're using a transformer to determine how many elements, so how many rooms are going to be in this layout, and certain constraints on their sizes and aspect ratios and things like that. And then a pointer network, which is going to determine which rooms should have constraints between them and what these constraints should be in terms of things like adjacencies and stuff like that. So we have this transformer and pointer network approach, which is going to produce this sequence of constraints that apply to individual room elements and also adjacency relationships between them. And then we execute that program, this constraint program, using a linear program solver. These constraints are formulated such that they're all linear, and you can use an LP solver to do that. And that gives us as output, finally, at the end of the day, we have a floor plan, which is connected, sort of is guaranteed by construction to respect the constraints that our generator produced. Okay, so I've showed two examples of systems that use a generative model to produce some constraint program, and then that was solved to produce the output. So for the last example, I'm going to give you a different flavor. So this is a paper, again, out of my group that we published at SIGGRAPH Asia last year on a system called shape assembly, which is a little language for modeling 3D objects by declaring cuboids, which represent different parts of the shape, and then attaching them together using attach operators or variants of the attach operator. And so the way that this pipeline works is, again, we start with a deep generative model. In this case, it's a variational autoencoder. This diagram is a little bit fancy, but basically it's a variational autoencoder that's going to sample a hierarchical program. So a bunch of lines of text where in some lines of text, they might actually expand into a subroutine, and so we then sort of fork off another node in this hierarchical program. But that's really all that it's doing. It's just start with a single latent variable that's normally distributed, and then decode into this hierarchical program. So the outputs from this generative model are these sort of imperative programs that sort of each line is a declaration of a particular, either a declaration of a particular part or some attachment operator that describes how these parts connect. And then to execute this program, we actually defined and wrote a little interpreter. So there's no kind of constraint solver or anything. It sort of immediately imperatively executes all of these statements to produce the final output geometry, which is this connected assembly of part proxies that represent the 3D shape. And then because these part proxies are only approximations of what the part geometry would look like, you can then choose to put it through some kind of refinement model that would use a neural network to actually synthesize more detailed geometry for each one of these cuboids, which in our case, we just sort of showed that you could do this with like a point cloud generative model, kind of a proof of concept for this pipeline. Okay, so I've shown 3 examples of this neurosymbolic modeling pipeline. And so now I think it's worth going back to the goals that we proposed earlier and ask, did we actually get the best of both worlds? Did we actually get a system that's easy to author, produces a high variety of output, high quality outputs by construction, and is something that we can read and interpret and edit? So we can take a look at these point by point. And I would say that in terms of ease of authoring, essentially what we've done is we've trained these deep generative models to write programs for us, right? We have each, the generative model, each sample from it is a valid program in the particular language that we're using to express our objects. And so I think, yeah, this is easy to author. We just have to add data to train the generative model, and then the generative model takes care of writing the programs for us. We don't have to be expert programmers, or even experts in this particular language. The generative model is the one that has that expertise. We can still get a variety of outputs, because even though each individual program, it has some set of parameters, it's only able to express a small subset of possible shapes. The generative model can then still sample many, many different programs. And so we're allowed to, the fact that the latent space of the generative model is capturing a high variety of output shapes. So here I'm just showing 3 example shapes that were generated for shape assembly: chairs, tables, and some cabinets. And so it's the exact same architecture. We didn't have to change anything about that. We just fed it different training data, and you can then get different output shapes this way. And we're showing here on the top and the bottom row the nearest neighbors of each generated sample in terms of its the geometric distance between them, or in terms of the textual difference in the programs that describes these shapes. Just to show that we're not just memorizing exactly what's in the training data. These things are generating different structural patterns than what they were trained on. So there's variety in that sense as well. So yeah, I think we got that. We can ask about whether we have high quality output by construction. And I would say that in some sense, we actually are doing better than prior approaches to generative 3D object modeling. So here again, I'm going to show an example from shape assembly, where I'm going to take an input shape, I'm going to interpolate to another shape by following a linear path in the latent space. And these pink shapes on the top are what would be output by StructureNet, which was the predecessor to shape assembly. StructureNet again, it's a hierarchical variational autoencoder, but it directly outputs the positions and sizes and orientations of these cuboids. And so what you can see is that it does eventually, transition from this kind of single flat surface back chair to one that has multiple slats, but it goes through some kind of weird intermediate states where parts are a little bit disconnected. And one of the nice things about shape assembly is that the programming language that we use, it actually creates these shapes by these attachment operators. And so basically all of the shapes that it outputs everywhere along this interpolation sequence, because they are valid programs in the shape assembly language, they must end up having parts attached to each other in some meaningful way. And so it doesn't suffer from the same class of failure modes when doing these interpolations. So that's really nice. We can also look at, I mentioned before in my motivation that these generative models can be really good as priors for vision systems. So we can look at trying to use either StructureNet or shape assembly as a generative prior for reconstruction from point clouds. So here we condition the model on an observed point cloud. And we basically train something that will project that point cloud into the latent space of either the StructureNet generative model or the shape assembly generative model. And then we can decode from that projected latent space point and see what we get. And you can see that both of them do capture the kind of bulk shape of the object. But again, StructureNet, because it doesn't have this inductive bias that parts should be connected, it ends up often producing kind of this garbage geometry. We have parts that are self-intersecting a lot or kind of floating off in weird ways. So it's basically the fact that the shape assembly language requires these parts to be connected. It kind of acts as a regularizer so that the output can't do certain bad things that it might have done otherwise. So I think that we've really made a lot of progress in this direction as well. And then we can ask the final question about how interpretable or editable are these kinds of these generative models. And so one thing we can do, here's an example of a little editing interface that we built for shape assembly programs. So every program that the generative model writes for us, we can then go in and we can actually edit any of its parameters to produce variations. So and we can tell that if I tweak this particular slider, it's going to have this particular effect, right? I have these nicely kind of interpretable, isolated controls over what the editor is doing. There's also some applications that we've done in the past for things like with Planet, we exploited the fact that we could take a natural language description of a scene that you might want to build, like give me a bedroom with 2 single beds and a lamp between them. With some very rudimentary natural language processing that's easy to convert into kind of a partial graph description. So this is like an incomplete constraint program. We can then feed that into our generative model to complete the program, and then run our backtracking search, our neurally guided search, to execute that program multiple times. And we can actually get different possible configurations, different scenes that satisfy this initial specification. So in this way, the fact that we actually had this symbolic program representation allowed us to provide more kind of semantic user control over the output of the final output scenes from the generative model. So I'd say that we've done pretty well here as well. So given that I don't know, hopefully I've sold you at this point on this neurosymbolic class of models as being valuable and worth pursuing. But so far I've painted kind of a rosy picture of like, wow, look at this, we solved all of these problems, we got the best of both worlds. So what's next? What's left to be solved? What are the big open problems in neurosymbolic generative models for 3D? And I've thought about this a bit, and I like to group these into what I call the 3 Ds. So 3 problems that all start with D. Hopefully that'll make it easy for folks to remember as a nice take-home message. And those are data, details, and DSLs, which is an acronym, for those of you who aren't familiar, for domain-specific languages. So what do I mean by each of these things? Okay, so what's the problem? What's the open problem around data? Well, if we look at these systems these 3 example systems that I introduced earlier in the talk, we can see that they actually have a pretty strict demands on the structural annotations that are in their training data. So Planet, for example, was trained on the SunCG dataset, which is this large repository of about 40,000 house scale indoor scenes, where every single one of these scenes has cleanly segmented objects, everything is category labeled, all of that stuff is provided, which is is not easy data to acquire. And in fact, the SunCG dataset is actually no longer available, so not even this data is available anymore. If we look at shape assembly was trained on PartNet. And so basically the training programs that we fed to that hierarchical sequence variational autoencoder were derived from PartNet hierarchy. So PartNet is a subset of the ShapeNet dataset, which has very, very fine-grained part segmentations. Every part is labeled. All of the parts are hierarchically grouped. So for example, a table lamp would decompose into the actual lamp head unit and the body and the base, and these things can further decompose into more subparts. So obviously not every 3D model out there in the world comes equipped with all of this structural annotation. And shape assembly really can only be trained on data that does have this information. So that's why we only really demonstrated shape assembly on a few categories of shapes that conveniently had all of these annotations in PartNet. But that's not terribly satisfying. I mean, we would like to be able to apply the power of these neurosymbolic modeling pipelines to arbitrary 3D data, from anywhere in the world. So what do we need to do to make that possible? Well, you can go out there and collect data and label it by hand, which is extremely, laborious and potentially expensive if you're, paying people to perform this task. So it's really important, I think, for us to look very critically at some of the recent work that's been done on unsupervised or weakly supervised shape segmentation. So you have systems like BAUNet, which uses this interesting property that if I train a generative model which outputs an implicit field representation of an object, and I train it where it has sort of multiple branches, each neuron represents one output SDF value, and I produce the final output by a max pool of these multiple outputs, that in fact, each branch will tend to learn to describe some spatially contiguous, consistent region of the object. And so if we give this just maybe a couple of labeled examples, we can often guide it to produce the segmentation that we want across thousands of shapes that it's never seen before, to, for instance, segment airplanes consistently into a fuselage, 2 wings, engines, and a tail. There's also systems like AdaCoseg, which look at learning a prior over what parts tend to look like in general. And then given some small labeled set of examples, we'll learn to segment a bunch of other shapes in a way that is consistent with the example set that was provided. That's great. We can also, I think it's also important to think not just about flat segmentations, but hierarchical decompositions, because this is something that, for example, shape assembly needed, and I think other systems are likely going to want this kind of data as well. So there has been some work on this in very recent years. There's this paper on learning how to take a single image and decompose it into an incomplete binary tree of primitives. I believe these primitives are superquadrics in this particular case. So this uses no supervision aside from just reconstructing the input image, and it produces okay decompositions. They're not necessarily semantic, but they might possibly be usable as annotations for a generative model. And there's also been work on, again, doing a similar concept, but here we're starting with 3D objects as input instead of images, and the abstractions we're using are cuboids instead of superquadrics. There's also, I think it's, we don't want to get too caught up in looking at the most recent stuff that was just published at, SIGGRAPH or CVPR or NeurIPS like this year. There is some older work on weakly supervised decomposition, which I think is also relevant. And I put older in quotes because it sort of pains me that this paper is from 2014. It's only 7 years old, but that's like ancient history, but at the pace that things move at today. So this was a paper that looks at using a probabilistic context-free grammar, which can be learned from a small number of examples, to take a 3D scene, which is inconsistently and over-segmented, and parse it into a consistent hierarchical decomposition. There's also work from 4 years ago that looked at how do we leverage large collections of 3D shapes that, again, have inconsistent decompositions. Some parts have labels, some parts don't. This is just sort of what you get if you look at raw data that's on things like the Trimble 3D Warehouse or TurboSquid or CG Trader or something like that. How can we kind of leverage all that information, sort of noisy, incomplete labels and parent-child relationships, to learn a consistent hierarchical shape segmentation and labeling scheme across all of the data? And in this case, so this prior paper, this one from 2014, was using grammar parsing. This one is using an expectation maximization, sort of alternate optimization, where you alternate between optimizing part labels and parent-child relationships conditioned on those labels. And so these approaches are not really using deep neural networks. Technically, this one uses like a pre-trained feature space, but they're not based on fancy neural network architectures. But I think there's a lot of value in revisiting some of these ideas, like grammar-based parsing, and particularly revisiting them in the context of all the new tools we do have available to us now, like all of the fancy deep net architectures that have been developed, and seeing if there are good ideas that we can sort of mine from some of these older approaches to identifying structure in shapes. And so I would argue that I think, if you're a new grad student who's listening to this talk, I would say there's a lot of work going on heavily supervised problems and building new data sets for doing more supervised learning. I would encourage you, not to spend your time working on those kinds of problems, but to spend your time working on these kinds of problems, on trying to discover this kind of structure without any supervision or with very little supervision, because I think it's really going to be one of the critical steps to taking some of these technologies that we've been developing and moving them out of the research lab and into the real world. Okay, so that's the first of the D's, about data. The second one is details. So what do I mean by that? Well, if we look at the output of shape assembly programs, for example, these are connected assemblies of cuboids, where each cuboid is a proxy for a part. And it's fairly blindingly obvious if you visually compare those to the shapes that exist in a data set like ShapeNet, that there's some interesting surface detail that's not being captured, right? That these cuboid proxies don't really quite cut it ultimately if you're trying to represent a high fidelity 3D shape for lots of different applications. So what do you do? Well, we saw that one thing you could do is you can try to train some neural network to refine each of these part cuboids into some higher detailed surface geometry. In this case, we just hacked together a solution with point clouds. You could also imagine doing this with implicit surfaces or meshes or what have you. But what about procedural details? Could we potentially not just generate programs that put together the structure of shapes and scenes, but also the actual geometric details that sort of give rise to the interesting surface appearance of these 3D entities? So one possible way to do this, you could think about, actually many parts of 3D objects were generated by programs originally. They were generated by CAD programs or modeling sequences in CAD packages like SolidWorks. And so it might be possible to, again, learn a generative model which can generate objects as these kind of CAD modeling sequences. What I'm showing here is an example of some recent work that I did with some collaborators on inferring a CAD modeling program from a particular input shape. This is not quite the same problem. In some sense, it's a lot easier because you're given the sort of target goal state. But they are related. And I think if it is possible to do this inference problem, it may also be possible to do the generative problem as well. So CAD modeling languages, or the kinds of languages that something like SolidWorks use, are one possible option. But this actually leads me to the third D, the third and final D that I want to talk about, which is DSLs, or domain-specific languages. And so the question here is, what is the right, or are the right languages to use for these neurosymbolic modeling problems? And all of the existing work that I just surveyed in this talk, these all use kind of specific handcrafted domain-specific languages. So in the case of Planet, we ourselves sat down and we thought really hard, and we said, okay, I think what we want is a language that has objects and it has relationships, and the relations encode, spatial relationships. Those relationships will have directions attached to them. Like, we kind of ourselves used our own domain knowledge to figure out what we thought was the right language for expressing this kind of structure. A similar thing was done in the generative layout modeling with constraint graph system. And in shape assembly, we again sat down and thought, okay, if we wanted to model the structure of 3D shapes, of kind of manufactured part-based 3D shapes, what do we think matters? Well, we think it matters that you can declare parts and you can attach them together. And so we sat down, we came up with a language that had useful operators for doing those things. And so these work, but the question is, are they the best languages? Might there be better languages for certain domains of 3D shapes or scenes? And could we automatically discover what the right domain-specific language is for a particular set or domain of 3D content? It's kind of a tantalizing question, and there's some really interesting work that maybe many people in this audience might not have heard of that I would recommend you take a look at. There's this paper from Kevin Ellis and his colleagues at MIT called Dreamcoder, which is this really fascinating system that they applied this to solving all kinds of program induction problems, like learning programs that can perform operations like list processing, how to compute the sum of items in a list, or how to abbreviate text, or how to build block towers, and how to filter lists and things like that. Lots of different domains of programming problems where the system was given input-output examples, and it tried to induce a program that would solve the problem. And what they did is they built this system where in the course of figuring out how to induce these programs, their system would learn kind of more and more complicated subroutines. Essentially, in order to figure out how to take the nth largest element of a list, it would first learn how to take the maximum element of a list. And in order to learn how to take the maximum element of a list, it first had to learn how to filter a list for a particular predicate. And so by first training the system on simpler problems, so it could build up these sort of more atomic library functions, and then gradually expanding into training on more complicated programs, it's able to build up more and more complicated library functions that it can then repurpose to solve more problems later on. It's really fascinating work. I definitely encourage you to take a look at it if you aren't familiar with it already. And we've been really inspired by this approach as well, and have been looking at, in some recent work, we've been looking at building a dreamcoder-like algorithm for trying to discover these kind of higher level functions within shape assembly. So we have this example where we've got a collection of, say, shape assembly programs for chairs. We feed this into, I'll leave it as a black box for now, this, some sort of method for doing function discovery, and it spits out, some set of higher level functions that we can use to model these chairs. So for example, one of the functions that it discovers is that a very common pattern that occurs is having this 4-leg chair base. And in fact, in the original shape assembly programs, a lot more free parameters were required to express the spatial configuration of those 4 legs. This little function that we've learned actually reduces it to just 2 free parameters, which govern things like the size of the legs and the relative positions of them along the chair base. And so we've been doing some experiments to show that, that if you actually train generative models on programs expressed in this higher level language, that they actually can perform better than ones that are trained on lower level programs. Because once again, these higher level functions are enforcing more of this sort of high quality by construction property that we really like to have. So I think this really is just the first step in this direction. I think that thinking about how to discover languages from scratch, where you only have very, very, very rudimentary like geometry construction operations, would be really fascinating, especially for looking at like the detail problem. How do we discover good languages for specifying procedural details and shapes? Okay, so these are the 3Ds. I just wanted to put them up here to remind you what those stood for. So figuring out how to do unsupervised or weakly supervised structural annotation of our 3D data, how to learn generative models, neurosymbolic generative models of detailed geometry, not just high-level structure, and then how do we discover what the appropriate languages are for modeling different kinds of phenomena in the 3D world. So there you have it. I'm just going to put this back up here just to remind everyone, this is what I think is the pipeline of the future for doing 3D generative modeling, and what the open questions are. And I guess at this point, I'm happy to take any questions that people may have.
Great. Yeah, thanks, Daniel. I think this is very exciting. And also, thanks for organizing your thoughts and suggesting these kind of very insightful future directions. So we have actually 2 questions, I think. The first is actually from Yasu. And the question is really long, but let me try to summarize it. Yasu, you can comment if that's not correct. But I think the main idea in Yasu's question is, you said we can use either supervised data, and those data are kind of very hard to obtain. And there's the data sets that you mentioned, unstructured PartNet or whatever structured annotations. And Yasu said there's another data set from Autodesk, like Fusion 360, yep, which seems to also have these kind of detailed code annotation. Yep. But alternatively, still these data are expensive and sparse and hard to obtain. So we can use more like unsupervised, weakly supervised approach, as you said, it's the kind of point 1 here. And so my understanding that the main question is, then do you have a sense of the performance gap between methods that use supervised or annotated code bases, or methods that use weakly supervised annotated data? Because weakly supervised data may be like more likely to have errors or noises. So would that really lead to a performance degradation if you use those kind of data?
Yeah, that's an interesting question. I mean, we haven't tried to do it yet because this is actually something we're working on in my group, trying to build some tools that allow us to do weekly supervised, basically with weak supervision, generate the kind of training data that we need to train like shape assembly generative models. So we haven't actually built that system yet, but once we do, that's definitely something we're going to want to look at. Is do you suffer any sort of penalty for using data that wasn't like rigorously verified by a person? And my suspicion is that probably you're going to be able to get away with quite a bit because in the case of shape assembly, at least, we didn't have the programs were not like manually authored by a person. We sort of heuristically extract them from partnet hierarchies, and so there's a lot of noise in that process as well. And the shape assembly generative models can often be robust to that kind of noise. So I suspect that as long as there aren't like massive systemic failures in the weakly supervised segmentations, that it probably will be reasonably robust to some small errors, but I couldn't quantify that for you right now.
Yeah, Niloy, go ahead. Yes. I think we cannot hear you for somehow.
Oh, Milo, it looks like you're unmuted now.
Yes, now it works, I think.
But we still can't hear you.
You can hear me now.
Right? There
yes.
we go. Yeah.
Yes.
Too many options here. So one question I had was, I really like the talk. I think the vision you have is really makes sense, and I think there's a lot of interesting questions to explore. There's one aspect where I'm a bit torn. Like there is this need for control that we are in graphics, we're in generative modeling. We want control at the scope of geometry or material behavior. That's a different thing that you did not yet touch on. But if we do unsupervised, maybe the machine can, let's call it the machine, it comes up with the language, it generates beautiful not rendered, like 3D model, textured model, etc. It's not necessary for it to come up with the language that is interpretable by humans.
Right.
I think so. The unsupervised, I think there is a tension between unsupervised and interpretable.
Yeah, no, I totally agree. I think that this came up with the work that I mentioned, where we were trying to infer these CAD modeling sequences, where this is something that you could approach with a paradigm like reinforcement learning, and people have. But when we were doing it, we trained on a bunch of supervised data, a bunch of modeling sequences that people had actually made, and we did user studies where we actually took, actually our participants were like actual CAD modeling practitioners, and we showed them like, here's a target shape, here's the different ways of modeling it, where one of them was like discovered by kind of an unguided like RL search type thing, and the other one was guided by this supervision. And we asked them like, which one do you prefer? And they do tend to like the ones more that are informed by what human design patterns. So I totally agree that we're never going to get rid of some need for that. And so I think that the question is just like, how do we minimize the amount of effort that it takes a person to express like just the right amount of guidance, so that the machine can then figure out how to automatically infer the right language, the right programs in that language. In the case of like the stuff we're looking at right now for weakly supervised hierarchical decomposition, we're looking at providing that guidance as a very small number of labeled examples, or perhaps a very small number of easy to express rules, things like that. But I think that's still kind of the Wild West. I don't really know what the right answer to that question is.
Do you think sparsity would be one thing that could help here? So if you have, for example, a large latent space, then each of these dimensions of the latent space would be a parameter. So there are many degrees of freedom, maybe too many, much more than you want. And do you think having some sparse description of the shape could help you?
Yeah, I mean, and that's something that that we've been looking at with the work that I mentioned on automatically inferring higher level shape assembly functions, where you need some kind of objective the automatic program discoverer is trying to follow. And one of the terms in that objective is trying to minimize the number of free parameters that the resulting program has. So it's kind of taking that like Occam, the sort of Bayesian Occam's razor kind of explanation that the more you can compress the representation, the more likely it is to be, the right one in some sense, getting rid of the extraneous degrees of freedom, which often works out to be the case, but I'm sure there are some examples you could concoct where there are many equally good, equally compressed representations, and some are more, semantically preferable to people.
That's true.
So, Daniel, this reminds me of, actually, we recently had a conversation with Manish on some of these, like how program representation can help visualization and interaction. Because then this reminds me, because the benefit of having an interpretable program like representations for structured content, either shapes or images or whatever scenes, is also it probably allows much easier user interaction. Because if I want to edit a scene, I want to edit a shape, it's much easier for me to change that program representations. And so are you interested in extending your current work, or maybe you're already doing that, or extending that to some interactive setups?
Yeah, well, we do have a an editor for shape assembly, and I think that there actually is. I think if you go to shapeassembly.cs.brown.edu, there actually is a running instance of that. It's a web-based thing that you can play with. Interestingly, the act of building that interface and running some user studies with it was very informative in the ways that our system is not as usable as we'd like it to be. Because I do think that in terms of the direction of interpretability and editability, that programs offer that for certain people, but I don't think it's not necessarily the right interface for everyone. I think regardless of interface, I think it's the right representation, because we've seen that from our experience that when you train generative models of programs as opposed to shapes directly, you get higher quality output geometry. The geometry tends to be more physically valid, more stable, all of these things because of the inductive biases of that language. So I think it's the right representation regardless, but I think it's only the right interface for certain people. And I think that some of the technologies that we've been seeing developing around, latent space exploration, I think about some of the work that like David Bao has been doing on DMU writing and stuff like that. I think all of those things are super useful modes of interaction. They'll continue to be useful in this domain as well, as sort of a different front end. But I still think that the back end, the representation, should still be this program, and that we should be learning how to perform, exploration and rewrites in the latent space of programs instead of a latent space of shapes directly.
So a related question is actually also, maybe that is because, here the programs, they focus on reproducing high fidelity object geometry. But when humans are designing those shapes, maybe geometry is of course part of it. But maybe, when we are thinking about how to make a chair, we also thinking about things like the functionality or affordances, whatever that means, people call it, right? So maybe those kind of program-like representations should really better capture the preferences of humans that they have when they're creating those objects, and not only the geometry of object itself.
That's true. And I mean, one of the reasons why shape assembly is called shape assembly is because it is in some sense an assembly language. It's like the lowest level language you might imagine for specifying shape structure. But I agree that might not be the right granularity to express it for different tasks. And like one thing you mentioned is you might, for example, have a declarative language for shapes, which says something about what kinds of parts need to be there and what kinds of functions need to be possible. And then you sort of rely on your solver to kind of figure that out for you. I think it'd be fascinating to think about, there's a huge gap between those two languages, obviously, right? That low level assembly language and then the one that allows you to express things at that level. How do you close that gap without having to have, a person come in and manually design every language along the way up, right? Can we somehow discover what the right languages are sort of from first principles? And maybe first principles involves things like simulations of sort of humanoid agents doing things with the object. That might be something we need to be able to do. But I think that's a fascinating open question.
Maybe I'll have a follow-up question. I think it again goes back to the unsupervised part, right? Like in the DSL work that you showed, the shape assembly, the choice of the DSLs regularize the space. So it does that. And it's same for Fusion 360. They have these sketch operation and the extrude operation, and the choice of this regularizes the space, right? But if you go to this more unsupervised domain, then I think it comes back to one of the things that you said, like such a representation does not generate bad models, but I think it's going to be fundamentally difficult for it not to generate bad models, because it needs to see or have some other mechanism to say this is not a valid chair, or this is so. But as Jay was saying, that probably by function or by affordance, there has to be some mechanism for it to discard objects, and it needs to be told that. Right now, in the unsupervised, we're only showing good examples. So how does it know or evaluate? It's not good.
How does it know what not to do? It only knows what to do, right? Yeah, it's interesting. Yeah, it's fascinating. I mean, I think that you can end up with, like, one form of weak supervision can be some form of preference about what function the shape needs to be able to support, the object or the scene needs to be able to support. And so there's two ways to go about achieving those goals. One is, you try to train your generative model with respect to some loss function that penalizes failure to satisfy those goals. Or I should say, you can try to bake it into your language such that it's impossible not to satisfy those goals, right? That it satisfies them by construction. And I think both are valid and valuable. And I think that what happened sort of before we started investigating these neurosymbolic architectures is that everybody was focused on the former. Everybody was focused on, how do I design better and better loss functions to try to make sure that the output has the properties I want? And I think one of the main, philosophical differences of this neurosymbolic approach is to argue that, wait a minute, if you just bake that into the language, then you don't have to worry about whether, some outputs will or will not satisfy the sort of desirable properties, because by construction, it can only do these things. Like, it can only output floor plans that are actually valid connected rooms, right? And so the kinds of properties, the kinds of guarantees that we're building into our languages so far are very low level, right? They're things like physical connectivity and stuff like that. And so really the big aspirational goal, I think, for the field moving forward is how do we make those guarantees higher level? So yeah.
I also going to, I think, go in a similar direction as I said before. So I think sparsity might also be an answer to that, right? So if you only use a small fixed set of primitives that you can use and a small fixed set of operations, I think then the need to represent all of the data in the data set with a small set of operations will make it harder for the network to learn things that allow it to go outside of this data set, right?
Yeah, that could very well be true. Yeah, I think that probably, sparsity or compressibility is probably the best unsupervised proxy we have for these things. And it's often what we fall back on at the end of the day. But I really like, I alluded to this earlier, I really like the idea of doing some sort of simulation of a person or an agent interacting with an object or a scene as another form. It's not exactly unsupervised, but it is something that in principle you could learn to do without somebody having to manually provide these interactions for you. Like, one thing that I think would be as a super moonshot sort of project is to say, okay, if you want to learn a generative model of a class of object that's supposed to be usable for something, how about you jointly learn at the same time, you learn a generative model of that object and a policy for an agent to use the object. And the two are sort of bootstrapping each other, right? The agent is trying to use the object, and the object is trying to be usable for the agent. Like, this is a really gnarly learning problem. I have no idea how to do this efficiently right now for anything. But I think that something along those lines could be a really, really fruitful direction to get at some of these higher level properties. And you could do it in the generative model training phase, or you could do it in the language discovery phase. And I think that that's a valuable direction to explore.
Maybe even half of that is quite useful, in the sense where the regularizer comes from the agent behavior at a high level. That's also given in addition to the DSLs. So
yeah,
it's not discovered, and it still can be.
Yeah, I
That's
mean,
the functionality that
in terms of how to make actual practical research progress, you probably want to start with assuming some things are given, and then gradually take the training wheels off, right? Yeah, I sort of gave like the grand vision of what you'd arrive at the end of the day. So yeah.
So actually, Daniel, what you said it reminds me of a paper actually from DPARC and Philip Isola and Alosha Efforts, where they're saying, okay, if you have where they try to combine agents or morph an agent so that the agent is like a connection of sticks or number of short sticks, but they can be connected in different ways. And then if the agent goal is to run or whatever in a reinforcement learning setting, then how can I actually come up with an agent whose shape is best suited for running forward as fast as possible, especially given so that seems like in some sense, right, this is like a simplified form of what you want to do. Yeah,
there really only was one actor, it was just the agent. And I think what I'm proposing is kind of like imagining that you have the actor is learning, but also
right, yeah.
Well, the environment is kind of, in this case, the environment is the object that the agent is supposed to interact with, or the scene that the agent is supposed to interact with.
Yeah.
And like all these things are theoretically possible with general reinforcement learning, but in practice we never work. So right, yeah.
There's a question from the audience that I think is also relevant. So as actually the question is basically, in some sense, Daniel, you already said that. So semantic structures is that possible to be really unsupervised? Right? It seems not really completely unsupervised because they're already driven by aspects such as geometry, functionality. But then the question is, if some examples are always required, what do you think? How can we think about the minimal set of examples, right? What are the new examples that would be most useful? Maybe in some sense that's like an active learning setup.
Yeah, and there may very well be, insights from active learning that can be given there. But I think also, I feel like most of the active learning literature is often pitched at kind of like decision-making, classification-y kinds of problems. And one of the unique properties of the kind of 3D generative modeling problems that we're working on is that you can look at the outputs. And so in some ways, I think one of the things that maybe has been under-investigated in this domain is just how to build systems where you can really efficiently visualize the impact of providing a new example and whether that is the right example or not. Of course, that's kind of hard because in the era of deep learning, all of our models take hours to retrain in response to new input. But there are some of these like meta learning, like learning to learn systems where you can basically say, you can train a model that takes a data set and spits out a new model, right? And so you can imagine something like that you might be able to throw into one of these like interactive, let me add a new example and let me visualize what it's going to do. I really think that visualization is sort of underexploited for this particular domain.
Maybe there's one paper that comes to mind, and I think some of you really remember this. It's ancient, but not so ancient. It's only a few years back at SIGGRAPH. It's this fit and diverse paper from Richard Zhang and Danny Koenar, which is, I think, a very interesting metaphor where the user is shown new examples, in your case, new chairs and new things, and they will say, oh, I don't like that. And that's a different form of labeling and maybe much simpler for the user to do, and without have to run the simulation that is the harder problem that we're discussing.
Yeah, it's like a form of weak supervision. Can you take weak supervision about sort of global preference and figure out like what locally needs to have been changed? I know there's been a little bit of work on this. I remember, I know that like Sid Chowdhury and some other folks had a paper when they were looking at just by training some kind of like global shape classification task, they could figure out how to automatically segment sort of salient parts that distinguish certain classes without actually having like segmentation level, like point-wise labelings. They were able to get that. So I think that's possible. It'd be interesting to think about different forms of preference that you could elicit from people. Yeah.
What do you think about neural rendering or neural representations, which goes a bit in the opposite direction, right? So making things less explicit, like meshes less explicit, materials less explicit.
Yeah, it is.
How does this fit together?
You sort of have like these two like seemingly at odds pushes, like okay, make things more symbolic, or like no, make everything just like a fully connected layer, right? You tell it what point in space, and I give you a shape. Yeah, I think it's interesting. I mean, I think that, and I remember there's actually a recent paper from Morgan McGuire and some other folks at like NVIDIA in Toronto on like efficient GPU rendering of these, these neural implicits, and like, oh, maybe we're going to have, maybe at some point we'll have fast, hardware support for rendering these things, and will they actually become supreme? I don't know. I still think it comes back to the sort of the nice properties I was mentioning about interpretability, about guarantees on what the output can and can't do. The way I see it is, I think that the kind of the neural implicit representations would be great representations for certain atomic parts of the 3D content, and what constitutes an atomic part may vary depending upon your application. It may be that you're building a 3D scene and you have some entire object, which is this neural implicit, but the way that you compose them and relate them to each other is through some kind of procedural representation. I think that, I don't know, that's the way that I would imagine these things playing nicely together.
Maybe there are some parts which you want to be able to control better, which you want to be able to understand better, and then maybe some parts that you don't care about so much. Maybe for some shapes you may want to have an exact or a good control over the coarse shape, good control over the position maybe of the shape, but less control over maybe small details on the shape or things like that. And maybe
that makes sense. And this goes back to this question of DSL discovery. Like, given that different applications will have different tasks that they actually want to support, in some ways it's not just a domain-specific language, it's like a task-specific language. Like, can you find the language that allows people to do the things they want to do, but then kind of delegates the rest of it to some neural representation that'll get you all of the fine details and stuff, and you don't need to worry about what's going on inside that black box.
I think there's also an opportunity in addressing the data axis that you talked about, like, because if you can do whether a DSL guided details like you showed, or a neural texture or neural procedure for adding details, but then we go back to the image domain, and now we have a very different richness of the data and volume of data. I think although we love ShapeNet, we love this new Fusion 360, we know it's super limited compared to the scale, richness, and diversity of images. It's much harder because cameras not known and others. But I think if we can connect this, and there has been some attempts in Platonic GAN and also in the NERF and also in the graph of connecting this, and also pixel NERF. I think there is an opportunity to do unsupervised, but then it linking the 2D and 3D. And
yeah, and I guess I should have mentioned in response to Paul's question about like neural implicits and where does that come in. Aside from as like a useful representation for atoms in your language, that's one way that it can come in. But also, yes, finding ways to learn stuff from image data is where I feel like these things are going to be most useful. I think that, yeah, Platonic GAN is very inspirational along those lines. And so it's interesting to think, if all you had was a large collection of images of a particular class of object, could you from that, figure out a language that expresses the 3D object that's underlying those things, right? That's quite challenging, because you have things that are sort of like nicely optimizable and differentiable, like ray casting or ray marching and these implicit frameworks, but then you want to introduce all these discrete structures about your discrete symbolic tokens. And I don't know how to do it, but it's certainly going to be something that somebody is going to look at in the future. If it's not me, I'm sure someone's going to look at that soon. Yeah.
Another question maybe also related to that. Do you think it would be possible or useful to have a single program that can express the entire distribution of these shapes or images instead of multiple separate programs?
It probably depends. I think it depends on the applications. I think that, if you want to give, like, if you're a programmer and you want the ability to manipulate a lot of shapes really easily, that's probably the right representation for you. Yeah, I don't know. I mean, we haven't really tried it. We don't really know what the trade-offs would be in terms of expressivity, in terms of quality, in terms of compactness. Because that is something that's interesting to think about. Like what we've done with introducing, kind of combining the neural and the symbolic is we've said, one way to look at it is to say, we started with deep generative models, which you had this latent space that captured all of the variability of the shape class. And now we said, no, actually what we're gonna do is we're gonna steal some of that variability and we're gonna represent it in the explicit parameters of this program. And so there is kind of this design space, this trade-off of how much variability do you steal and put in the program, and how much do you leave in sort of the uninterpretable latent space. And again, I think it's often going to be task specific. It's going to be dependent on how many interpretable degrees of freedom do you need to expose, or how much, or even if it's not about editability, it's just how much granularity do those programs have to have in order to encode the right inductive biases for getting good output geometry. You know, there's not going to be one valid answer, I think, you know.
I think there are also different ways to split it, right? You could split it into different parts of the data set. You could split it into different parts of the hierarchy, maybe the coarse ones.
Yeah.
With a symbolic representation, like one program and then different ones for.
Yeah, for sure.
Yeah.
There's really, I mean, I know I presented this pipeline with like lots of boxes you could fill in, and there are other axes that we didn't really mention that I know that you just touched upon. Like, there's a really huge design space to explore here, and as far as I know, you know, I just called out like three pieces of work that I think are representative of this pipeline. I don't really know about many others that I think would fit, and if people know of others, I'd love to hear about them. But I feel like, you know, I'm aware of like 3 dots in this massive design space, and there's a lot of.
Maybe I can give you one more.
Yeah, please do.
Which is not in shapes, but going from images to vector. I don't want to. There are some works on archive where it doesn't require vector supervision, but that's another way, right? Like when we go to vector graphics, whether in fonts and others, this is a different language, and there the DSL is DSL of splines.
Right.
That's given, but then it's again like, how do you find a language in there?
All right. Yeah, because again, splines is kind of an assembly language for curves, and presumably for most kinds of shapes you might want to represent that way, you'd probably want a higher level language, right? So yeah, that's interesting.
So yeah, very interesting. Daniel, I have a related question regarding you're saying like DSL, you know, dreamcoder and stuff. So there's a recent archive paper, I think from DeepMind, called Symbolic Behaviors in AI. I don't know if you've seen it.
I haven't seen it. No.
Okay, yeah, but I think it's more like opinion paper, where in that paper they actually had kind of some different opinions on it. I believe, my understanding, my interpretation of their words is they're saying they feel like dreamcoder is not going to work out because because, you know, the especially expanding DSL and those parts is you know, they say it is true that, you know, current results are still on more like, you know, toyish domains and relatively simple DSLs, and seems, you know, far away from capturing the rich DSL if they exist of the world. And they're arguing, okay, maybe you want to think about symbolic, whatever that means, from a totally different way. That is, okay, you know, we should, it's more like, what are the behaviors that agents or any intelligent systems will exhibit after training? And, you know, maybe it appears that this person is doing something after training, and that is, you know, you want to define that as more like a symbolic behavior instead of enforcing those kind of top-down, like some grammar rules, and you expand the DSL. So maybe you want to think about symbolic in a different way. So I'm curious, you know, how would you think of this?
So symbol is like a post hoc explanation of what the model has learned, as opposed
to. I haven't read that paper in very detail. Yeah, but that seems to be my understanding.
Yeah. Well, I guess maybe the broader question here is like, of course there are going to be some people who push back on this general direction, and I think, I mean, some of it may be valid science, some of it may be marketing, people who are sort of invested in, you know, deep nets end-to-end everything all the time for all problems. And, you know, there are other ways that, you know, like deep nets are being made more symbolic that don't look like what I proposed. You know, there are things like, you know, like neural Turing machines and differentiable computers, and, you know, trying to basically make neural nets be able to perform operations that look more like classic algorithms, but the whole thing is still end-to-end trainable. I mean, that's an interesting approach as well. I think let's see. So I think that it obviously is still difficult to get the right symbols, and really the hard problem is kind of connecting the real world, the raw percepts to the symbols, and so I don't know what approach is gonna win out at the end of the day. I mean, this is why it's great that we have people with different philosophies who are pursuing different things, and there can be cross-pollination of ideas, and maybe there's some disagreement, but I think it's all ultimately good for the field. I also would say, I guess if I can make like a brief advertising pitch, that if you like this direction of research, whether it be in graphics or vision or reinforcement learning, or I mean even natural language processing, there are a lot of people, a lot of my colleagues at Brown who are also looking at connecting neurons and symbols in in NLP and robotics and things like that. Like learning symbolic descriptions of high-level robot skills, or trying to understand how the patterns that GPT-3 is learning are actually related to sort of symbolic rules from grammar that we actually have. So yeah, if that's something that's exciting, you should come work with us. Okay, pitch mode done.
Yes, we do read a lot of papers from Brown. Also in robotics as well. Yeah, planning and stuff. I have a final question. And that is, these days, I guess partially people are arguing more like end-to-end approaches also because we have seen a lot of successes, especially recently on those kind of large-scale pre-training models on vision and language, and now jointly, right? Like DALL-E and CLIP and those kind of image generation, like a very fancy. Partially, I think this is, that makes me wonder, do you think it is possible for us to also have some pre-training models, not on images, but on 3D data? Well, maybe that's also related to your question on data, because data are hard to obtain, and all you have is a ShapeNet, which is maybe great, but not as realistic, but more accurate data is just, you don't have that. But would that be possible eventually to have some pre-trained models on 3D, maybe with the help of image data, as we said, doing inverse rendering, neural rendering?
I don't know. I think it depends. I mean, one of the things that sort of makes this more possible to have like the standard pre-training for images and text is that there's just really one representation for images and text. You have like you have your grid of pixels and your sequence of tokens, right? And in 3D, one of the things that makes it so fascinating is there's so many different valid representations that all have different trade-offs. Whether you're talking about meshes or sign distance fields or occupancy grids or point clouds, right? There's so many different representations that seem kind of difficult to imagine. I will say that on a smaller scale, there's definitely instances of this kind of pre-training. Like one of the weakly supervised segmentation methods that I mentioned, this Ada CoSeg paper, they basically pre-train and they assume that they have some large data set of part segmented objects, but they don't care about the semantic categories, and they're just learning a representation, which is like, what does a part typically look like? Where do objects tend to break down into parts? And then they use that as a pre-trained prior to then, they bootstrap that with a very, very small number of labeled examples to sort of co-segment shape collections based to be consistent with those examples, but also to obey the prior of where parts tend to be composed. So that kind of thing is already happening in sort of a smaller scale. It's not like, billions of parameters and like, consuming the carbon emissions of like 14 people in a year to actually produce the pre-training, but it's happening. There's actually one other thing I wanted to mention. I forgot to mention this in the response to your previous question about the DeepMind paper pushing back about symbols. One of the things that I think is great about these symbolic representations is that if you've got the right program, that the program generalizes arbitrarily. It sort of extrapolates in a way that, deep nets, like, yes, they do lots of magic stuff, but you look at them, you squint at them really hard, and really all they are is a fancy form of interpolation, right? They can't learn anything more than that at the end of the day. And so when you start to feed it inputs that are sufficiently far outside of its distribution of expected inputs that it was trained on, it's not going to generalize. Like, it just can't. And if you look at these symbolic representations, programs where you have something that, you infer a program, like a recursive program for processing a list, it's going to work on an arbitrarily long list. It does not matter, if it's like thousands of entries longer than the longest thing it's on its training data. So I don't quite know what the analogy for that is in representing 3D stuff with programs, but I'm sure it's there. We just have to find what it is. So I think in terms of as a representation for like understanding and reasoning, this is definitely the case. I'm not sure where it comes into play and when it comes to the generative side of things. But I think that's a powerfully compelling reason to prefer these kinds of symbolic representations. And I don't know, maybe those DeepMind folks would have some counter argument for that too. I'd be curious to hear what it is.
Great. Thanks. Yeah, that's very inspiring. Thanks, Daniel. And yeah, I think we're basically running out of time. So thank you again, Daniel, for the fantastic talk and the discussions. Thank you, Niloy and Paul, for joining us for the panel discussion. Yeah, so I'm going to end the YouTube stream right now, but then you can also watch the video afterwards. Great, thanks.
Thanks for having me.
Thanks, Jejun, for hosting. This was really good. Yeah.
Thank you.
Yes.